Thank you very much. I appreciate the opportunity to speak here. Please stop me at any moment if you're not able to understand what I'm saying, or if you have questions, or if you hear the police, or any other thing like that. So this is a joint work with René Rohr, who's a postdoc at the Weizmann Institute, and Yotam Smilansky, who's a postdoc at Rutgers. And so I will begin the talk by sort of explaining roughly what we do without getting into details. Then I'll give a bit of a historical motivation, and then I'll go back and get into more details. So the object of this discussion is so-called cut-and-project sets. Cut-and-project sets are a certain model for aperiodic order, they're sometimes called, or quasi-crystals, and they're defined as follows. You fix the following data. You fix dimensions d, m, and n, where n is d plus m. You fix a direct sum decomposition of Euclidean n space, where one summand is called physical space, and this is noted here, and the other is called internal space. They are of dimensions d and m, respectively. You have the corresponding projections related to this direct sum decomposition. L is either a lattice, all of you know what a lattice is, or a grid. A grid is just a translated lattice. And then you fix a window set W in the internal space, and then you project this intersection to physical space. So the set you're interested in lives inside d-dimensional space, inside physical space. So here's a picture explaining this. All the data that I had before are still on this slide, but now there's a picture. The picture is in 2 dimensions, so n here is 2, d and m are both 1. Physical space is this diagonal line running through the picture, a one-dimensional space. Internal space is the orthogonal line here. The cut and project set are the blue dots along the line, so you're seeing that they're not a periodic set, although they seem to have some weak kind of periodicity. And they're constructed as follows. The black dots are the Z2 lattice, the standard lattice. W is this red line on internal space. So this pre-image of W here is this strip. You intersect the strip with the lattice, that's the cutting part, and the points that you get after cutting are visible here along this staircase type line, and then you project all those points down to physical space, and that's your construction. So this is a famous construction and well studied, and I'll say more about the history in a moment. The most famous example comes from the Penrose tiling, which has 2 alternative presentations or 2 alternative definitions. I'll remind you, not least because Penrose was recently a Nobel Prize recipient, so we should remember one of his mathematical contributions. So here is the famous kite and the famous dart, and they're decorated with these red and blue circular lines, and you have a gluing rule which says that you can glue darts to kites edge to edge, or to either to the each to the other or to themselves, but you must make the red and the blue lines glue to themselves. And so in other words, I'm not allowed to reflect this dart and glue it here, because then the red line wouldn't match up properly. If I were able to do that, then I'd fill up a kind of a rhombus, and this rhombus would tile space periodically. And Penrose's discovery was that using these 2 pieces, you can you can tile the plane, but only aperiodically. So this is kind of a very nice example of an aperiodic tiling. And the connection to cut and project sets is that when you have this tiling by the kite and the dart, or various related constructions due to this tiling, then the vertex set, the points that you see as vertices of these tiles, can also be presented as a cut and project set. So that's a result of De Bruyn from the 1980s. And here's a picture of the resulting tiling of space. Hopefully I can zoom in. Yes, I can zoom in. So this is what you see locally in space. And for the purposes of the lecture, I just want to, let me zoom in even further. You're going to see eventually kites and the darts appearing, and you're also going to see the red and the blue lines matching up. And what's important is that you have several different, quite different local pictures. So for example, the picture that I'm putting a circle around will be called a patch later, and it's rather different from the picture that I see if I circle around this point or around this point. So there's a variety of local sceneries that you see, and these are called the patches, and they'll play a role later on in the lecture. So we're interested in the geometry, large-scale geometry of this type of discrete set. And we're only interested in the vertex set, in other words, the discrete set itself, and the tiling here is just to set things up and to make nicer pictures. So here are the questions that we want to answer in this project. We like to describe probability measures on collections of cut and project sets, which are affine group invariant and ergodic. And in this direction, our main result is a complete classification of these measures. So what do I mean by affine group invariant? So this is a probability measure, so it's a way of randomly choosing one cut and project set out of a whole collection. And it should have the property that the probability of choosing one particular cut and project set is the same as the probability of choosing its image under an affine transformation. What I mean by the affine group is affine transformations of physical space which preserve volumes. So a semi-direct product composed of translations and linear transformations with determinant 1, plus minus 1. And the second question that we want to understand is, once you have fixed such a measure, what does a typical cutting project set look like for with respect to this measure? And in this direction, when I say the words look like, what I mean is I'd like to have results explaining the frequencies of points inside certain large subsets of such a cut and project set, and for both points and also the frequencies of various patches. So this is a kind of a typical question about the large-scale structure of such a discrete set. So let me give a few more details about the spaces of discrete sets. We're going to be discussing measures on spaces of discrete sets. So we're going to do that by first setting up the sigma algebra. The sigma algebra is going to be the Borel sigma algebra with respect to a certain topology. And so what is this space and what is the topology? Curly C of RD stands for closed subsets of RD. It's a huge space made of lots and lots of sets. All closed subsets are points in this space. And we can topologize it with a certain metric, and then, which I'll describe in a second. And then once we have a discrete set, we can look at its the orbit closure under translations. So every set can be translated, and we can make orbit closures with respect to a natural topology. And these kinds of set omega are called tiling spaces in literature, and they're dynamical systems with an RD action. And to explain the topology, here is the definition of a certain metric, sometimes called the Chaboty-Fell metric. The distance between two points are close to each other, so the sets here are y0 and y1. They're both closed sets. 1 minus I here just flips between 0 and 1. So y0 is close to y1 if when you intersect it with this large ball around the origin. Epsilon is a small number, so this is a large ball. You take the intersection of y1 with a large ball around the origin, every point you see is within epsilon of a point of y0. And this also holds when you flip the roles of y1 and y0. Okay, so this is a kind of an obvious natural metric on spaces of sets. And if you look at the space of closed sets, with this metric it becomes a compact metric space. And the closure operation that I'm mentioning here could be taken with respect to this particular metric. The metric itself doesn't play an important role in what I'm going to say, but it's the easiest metric to define. And when sets are nice, for example, discrete sets with certain properties like finite local complexity and so on, many of you are probably familiar with those settings. This topology coincides with the other topologies that people use in the literature. So this is not an exotic topology, it's the natural topology to use. as I said, I welcome questions if there are any, so please stop me whenever you have a question. So in the literature, so I'm going to be discussing renormalization by the action of ASLDR. As I said before, ASLDR is the group of affine measure-preserving transformations. But typically in this business, the renormalization that's usually used is by dilations, by the positive real numbers acting by dilations. And the importance of this dilation action, I just want to review that slightly quickly, is that it renormalizes the dynamics by translation on the tiling space. So here's the idea in a nutshell. So here's a way, a kind of a classical way to construct tilings. This is the notion of the substitution tiling. We have a collection of 3 triangles with 3 colors, and we have a rule which replaces each one of the triangles with a bigger triangle inflated by some fixed inflation constant and subdivided back into the original shape. So here we see the big tile corresponding to the green, to the dark green, is partitioned into 2 copies of the dark green triangle, 2 copies of the yellow triangle, 1 copy of the light green triangle. And when you have this kind of rule, you can use it to construct a tiling. Here's a tiling that you can obtain by applying this rule repeatedly. So it's a part of a tiling of the infinite plane. And this tiling is naturally hierarchical. So you can think about dilating it, which has the effect of zooming out. So you look at it from further and further away. And because of the tiling rule, the edges are going to, if you remove some of the edges and keep others, you're going to see the same tiling with the same tiles on a bigger scale. So in a sense, this dilation dynamic or this zooming in dynamics will have recurrence. And when you have recurrence for the dynamics of zooming in, that gives you lots and lots of information about the dynamics of the translation action. That's one way to prove unique ergodicity and many other counting formulas and many other related things. So this is sort of the classical point of view of zooming in dynamics or dilation dynamics for renormalizing in order to understand the tiling spaces that are related to substitution tilings. But for cutting product sets, we do something else. And this is the ASLDR renormalization. So we're interested, so as I said, ASLDR is the semidirect product of SLDR, the determinate one linear transformations of R to the D and the translations of R to the D. And you can use this group to renormalize the space of closed subsets. Obviously, this group acts on RD, so it acts on closed subsets of RD. And if you understand the dynamics of this group, you're going to be able to understand individual point sets, and you're going to be able to understand the geometry and the RD action on these tiling spaces. So this is a relatively recent point of view in the literature. It was first used by Marklof and Strömbergsson in a sequence of very beautiful papers. So I left out the words very beautiful, but they are really beautiful papers of Marklof and Strömbergsson. And they use this dynamical system to address certain questions in statistical physics, in mathematical physics. I also want to mention some of my own work with Solan and Solomon. And we also use this kind of renormalization or this kind of dynamics in order to get partial results on the dancer problem. So the dancer problem is a wide open classical problem in discrete geometry from the 50s. We haven't solved it. It's still widely open, but it's a beautiful question. So let me mention it for those of you who are not aware of it. Dancer is asking, does there exist any set in R to the D, which is a discrete set, the number of points in a ball of radius t grows up to constants like the volume of the ball, and the set, so this means there's not too many points in the set somehow, but on the other hand, there are sufficiently many points so that this set intersects non-trivially every convex subset of RD of unit volume. This is a wide open question. It's been open for a long time. We haven't solved it, but we've shown that one way to attack it is to understand this action on the space of closed subsets of R to the D. If you had such an example, maybe you don't believe that such an example exists. If such an example did exist, its orbit closure under this group would have very strong properties that this action specifically detects this property of intersecting every convex set of volume 1, precisely because this group of affine transformations preserves the collection of convex sets of volume 1. Okay, so this was just a kind of a advertisement for this ASLDR renormalization direction of study. And specifically, Marklof and Strömbergsson asked two questions about this ASLDR dynamics. First question is, can we describe the invariant measures, which are supported on discrete subsets? So, as I said, this collection contains all closed subsets. The discrete subsets are some kind of a subset of this space, and they want to know which invariant measures there are one can put on this collection. And a more refined question, given such a measure, mu, and given a point in its support, is the following true? So what is this statement? Maybe it's easier to parse this information when you think about the SL2 case. So K lives in the group SODR, so you might take it to be the group of rotation. So this is just a circle. A circle, we're taking our set and we're rotating it through a circle's worth, and that's giving us a measure. And then we push the measure by diagonal matrices. And so the circular action becomes a kind of a long ellipse, and we're sampling the collection of closed subsets by performing this operation to our fixed base point y, and we want to know whether it samples mu fairly. It's a kind of an ergodic theorem for a big group, the group ASLDR, with these kinds of averages, and we want to know whether there is such a ergodic theorem and for which specific points does it hold. So this is definitely a difficult and technical problem in dynamics, and it turns out to be a crucial problem for the applications in statistical physics that Marklof and Strömbergsson are interested in. And so you might wonder if there are any such measures satisfying these properties. And Marklof and Strömbergsson showed that there are, and they are supported on, the discrete sets that they're supported on are cut and project sets. And this, their construction relies on homogeneous dynamics, and specifically it relies on a very famous body of work by Ratner from the 1990s describing doing the measure classification for actions of groups generated by unipotents. Ratner's work is used twice. The first place it's used is just to construct the measures. You're going to see that in a moment. And the second place it's used, which I won't talk about today, is to prove this, understand exactly this kind of equidistribution phenomenon. So here is the construction of Marklof and Strömbergsson, and since it's introduced by Marklof and Strömbergsson, it relies strongly on the work of Ratner. We're calling it, in this joint work, we're calling it the Ratner-Marklof-Strömbergsson measures, and it's going to be, the abbreviation is going to be RMS. So these are what we call RMS measures. So what do? You fix the dimensions of your cut and project. This is a measure supported on cut and project sets. You fix the dimensions in the cut and project instructions. You fix the direct sum decomposition, physical space and internal space. You fix the window. So the only data in the construction that I have not fixed here is the lattice that was used. The lattice L, or either the lattice or the grid. Now, with this data fixed, you consider the following embedding of ASLDR, affine maps of d-dimensional space, into ASLNR, affine maps of n-dimensional space. Here's the algebra of the embedding, V is the translation, G is the linear transformation. What you should think about geometrically is inside R to the D, inside R to the N, you have physical space as a d-dimensional subspace. And you just let the affine map move things in physical space without touching internal space at all, acting trivially on internal space. So that's the meaning of this embedding. Once I've fixed this embedding, I can consider the space of grids. This is a homogeneous space for this group ASLNR. And on the space of grids, suppose I could find any measure, which I'm going to call mu bar, any probability measure, which was invariant under the ASLD action. This group, via this embedding, is acting on n-dimensional space, because these are n by n affine transformations. And so I take such a measure, mu bar, on the space of grids. Such measures are associated with certain groups H, which are intermediate between ASLD and ASLN. That's the important work. That's the Ratner measure classification theorem. And given such a measure, mu bar, what you can do is you can project it to a measure on cut and project sets, because you have a map that sends your grid, L is the grid, L is an element of this space, to the set lambda LW, which is the cut and project set constructed from this data, including W, and from the grid, as in my first slide. Okay, so this is an important construction. I hope I've made it clear what the construction is. If there are any questions, as I said, please stop me. So this is the construction of Marklof and Strömbergsson. And I want to sort of give you a teaser of the things we prove first, and then mention a conjecture. So the first thing we prove is that any measure, which is ASL dr invariant and ergodic, and if suppose the measure gives full mass to cut and project sets, is one of the measures I just described. There's no other way to put a measure which is affine invariant and ergodic, and with probability 1 produces a cut and project set. And there's a technical condition on the cut and project sets. They should be irreducible. Irreducibility for the experts in the audience means it's a standard assumption in the topic of cut and project construction. So irreducibility means that for almost every L, the projection onto internal space is dense, and the projection onto physical space is injective when restricted to L. And so that's our first theorem. And I want to just mention a question. The question is there any other interesting construction of a measure, not just on cut and project sets, but more generally on Delaunay sets? A Delaunay set is a set that's uniformly discrete, so the distance between any pair of points is at least some positive number, and it's uniformly dense. There are no arbitrarily large open patches without any points of your set. So my conjecture is that any ASL-dr invariant and ergodic measure, which assigns full measure to Delaunay sets, again, Delaunay sets is a much wider class than irreducible cut and project sets. Any such measure, well, I wrote has a non-trivial joining with an RMS measure. Just as a first approximation of the conjecture, just ignore the words joining. Is it true that any such measure is actually the measure that I described on the previous slide? Now that's not exactly true as I just stated it. What you can do is you can take a measure that's constructed as in my previous slide, and then randomly, in a smart way, you can randomly add more points without destroying this uniform discreteness property, and without destroying the invariance and ergodicity under ASL-dr. So that can be done, but that's somehow cheating. So in a sense, I started with a measure which did come up according to my construction, to the construction I just outlined. So again, so this discussion about the joining is a statement for which I have no counterexample, and that's the conjecture. The only way to construct such measures is using the construction I just outlined. Now, I don't have very strong evidence for this conjecture. The only evidence that I have is that I tried, several times using several different ideas to construct such a measure, which is supported on this collection. And you should remember that this ASLDR group is a big group, and well, I wasn't able to. And if you think, I'd be happy to be proved wrong if you have a counterexample, but I find it challenging to envision any counterexample to this conjecture. Okay, so that was basically giving you an idea of what we care about and why, and I think this conjecture, if proved, would have very strong consequences for both problems in mathematical physics, for the Dancer question that I discussed, and other problems about discrete geometry. So I don't think it's a kind of a curiosity. I think if it's true, it's quite a strong result with a lot of consequences. Having said that, let me move on to our results, which are not yet at all close to proving this conjecture, but this was, motivating the things I'm interested in. So now I want to talk about our results in more detail. So from now on, theorems will be numbered. I'll just point that out. So if a theorem is numbered as it is over here, that means it's one of the theorems in the present paper. So the second theorem is a classification of the RMS measures, meaning Marklof and Strömbergsson said that the measures could be described using Ratner's theorem, but they didn't actually nail all of the data that comes up in Ratner's theorem. The data in Ratner's theorem involves closed orbits for certain groups, and we give a list of the groups. That's the content of theorem 2. So whenever we have an whenever we have an ASLDR invariant measure, we know by Ratner's that it's H invariant and supported on a closed H orbit. And here is H. It's given by our theorem. H has the structure of a semidirect product. In the semidirect product, the group of translations is the entire group of translations in Rn. It can't be any smaller. And the semisimple part, H prime, has a description in terms of restriction of scalars from a group defined over Q. So these are notions from the theory of algebraic groups, and I'm not planning to go into them in detail, but what you should notice is that there are only two cases, and they give you strong conditions on the relationships between between D, which is the dimension of physical space, and N, which is the dimension of the total space. And one of the two cases, the symplectic case, is also only possible when D is 2, when the dimension of space is 2. So somehow, if the dimension is larger than 2, the only case that can arise is coming from SLK. I'll give you an example now. So here are the 3 examples that can come up in the simplest non-trivial case, which is when D is 2, M is also 2, and therefore N is 4. The first case is somehow the big measure, the measure of biggest support. So the group H is the entire affine group of 4 dimensions, SL4, semidirect R4. The measure is the canonical ASL4R invariant measure on the space of 4-dimensional grid, which I'll denote by this M of Yn. N is 4 here, and that's the first case. That's the big measure, so-called. There's an intermediate group, an intermediate measure, which lives on block matrices. These are 4x4 matrices, and they're being divided into 2x2 blocks, and these are associated with real quadratic fields. And I'm giving you an explicit example, an explicit construction of the grid or the lattice that will appear. If you want to use this group, you can't just use it. You need to find a suitable lattice, and this is the lattice. So it's very, very number theoretical. It involves this conjugation in this quadratic field, and the Penrose vertex set can be written in exactly this form. So in the Penrose case, it's exactly case 2. And the third example possible in this dimension is the symplectic case. The group H is the symplectic group. And the lattice is a symplectic lattice. It has a basis which is a symplectic basis of four-dimensional space. So this is the sort of an example of how the classification works in dimension 4. In dimension 2 with n equals to 4. Now I'm going to give you a crash course on the Siegel summation formula, which is, what is the Siegel summation formula? The Siegel summation formula is a certain formula that was developed for studying lattices. And what we're able to do in our project is to prove analogous results for the measures on lattices for these RMS measures which we've just introduced. We have a bunch of formulas which I want to describe. So they're all analogs of work done, classical work done in the 40s and 50s. So here's the classical Siegel summation formula. Curly X of n here is the space of lattices of covolume 1. Given a function on Rn, you form a new function on the space of lattices, whose value on a lattice L is the summation over all lattice points, all non-zero lattice points, of the value of the original function f. Okay? So, for example, if f were the indicator of a ball, this would be just counting the number of points in the intersection of the lattice with the ball. And the Siegel summation formula from 1945 says that up to normalizing by a constant c, we have this beautiful identity. The integral of the original function f on Rn is the same as the integral of the transform of f hat on the space of lattices. And so this is a quite important formula for it's used in essentially, it's used because the measure on the space of lattices is quite hard to work with in practice, and the easiest way to work with it is through this identity. And one of the beautiful things done by Marklof and Strömbergsson in 2014 is that they extended this formula, replacing the measure on the right, the measure on the space of lattices, with an arbitrary RMS measure, mu, where the transform, instead of summing over all non-zero lattice points, you sum over all points in your cut and project set. Okay? As you see, I've written down the Marklof-Strömbergsson result in this purple color. From now on, the results which are analogs of classical results will be written in black, and their analogs will be written in this purple color. So this is the Marklof-Strömbergsson analog of the Siegel summation formula. A further classical summation formula is a higher dimensional one. So I've copied the original Siegel summation formula here, and I'm defining a new higher dimensional analog. You fix another parameter p, and then instead of summing your function on vectors in your lattice, you sum over p tuples of p different vectors in your lattice, and therefore the function f depends on p times n numbers, which I think of as p vectors in R to the n. And so this is the pth Siegel transform of your function f evaluated on the lattice L. And there's an analogous formula where you recover the integral of this pth Siegel summation from certain obvious measures on Rn to the p. For example, the Lebesgue measure on Rn to the p, or for example, measures supported on pairs of linearly dependent vectors or p-tuples with a certain kind of integer linear dependence, and so on. So there's a kind of an explicit formula which is too complicated to write down, which was proved by several people, and that's the analog of the Siegel summation formula. But before stating the Siegel summation formula, one more thing you want to know is this function in L1, is it integrable, even integrable, just to get the conversation started? So the first results in this direction are due to Rogers and Schmidt from the 60s, and a strengthening is due to Eskin, Margulis, and Moses. I didn't have room on the slide for their names, so that's EMM. So here's what they prove. If p is an integer less than n is the dimension, then this transform is an L1. Sorry, yeah, then this transform is an L1. And a sharper result is if you take any q smaller than n, so q need no longer be an integer, it could be any real number smaller than n, and you look at the original Siegel transforms written here, then its integrability exponent, it's an LQ. So, and this is sharp. So the largest, so for any q strictly less than n, f hat belongs to LQ, and as soon as q becomes n, I didn't write it down on the slide, as soon as q becomes n, f hat is no longer going to be an Ln. That's more or less classical, except for this new contribution from the 90s. And we get the analog. So we have the same two results for integrability bounds of the transform in the case of cut and project sets, except the parameter n that appears here and here has to be replaced with this number, 1 plus the q rank of the group H prime that I had in the previous slide. So that's a algebraic group theory invariant associated with this. And as an interesting corollary, what you can see now is that if I fix the dimension d and I use different measures involving bigger and bigger n, I can make this quantity larger and larger. In particular, it means that for larger and larger d, I can find analogues of this Siegel summation formula with better and better integrability bounds for the transform. That's an interesting fact that's can't be done for lattices. We have more flexibility for cut and project sets. As I said earlier, once you have this p-th transform, you can try to write down an identity for it. And so this was done in the 50s and 60s by Rogers, Schmidt, and Andreve in separate work. And as I said, they have combinatorial formulas for expressing this quantity. And we have the analog for RMS measures. We have kind of an infinite sum which expresses these expressions. And they also give us an expression for the higher moments of the original Siegel transform. And the shape of the measures that appear the flavor is given by kind of a cut and project type construction for the Lebesgue measure rather than for the discrete measures. Another thing we prove is something called the Rogers second moment bound. So for lattices in the 50s, Rogers proved the following fundamental fact. This expression, which is the second moment of f hat, if you fix f and you think of this as a random variable depending on the choice of the lattice lambda, then this is the second moment. And Rogers bounded the second moment in terms of the space integral of f, which is, as we saw earlier in the Siegel summation formula, this is actually the first moment. It's the expectation. So the second moment is bounded by a constant times the expectation. That's a very important input to counting results. And we prove the analog theorem in the full context of an arbitrary RMS measure. And using this as an input, we're able to do something that Schmidt did in the 60s for lattices. So what did Schmidt do for lattices? You start with any collection of sets, which we call an unbounded ordered family. So what this means is the sets are parameterized by positive real numbers. And when you have if you have T1 less than T2, then the corresponding sets are contained in each other. So an example to think about is just a growing collection of balls, Euclidean balls. But this could be a much more complicated example. You could, take kind of a strip growing larger and larger, or some kind of spiraling bodies, or whatever you want. It's just an unbounded ordered family of sets. And all you require is that they're each individually a finite volume, but their volume is increasing to infinity. And in this setup, Schmidt discussed the typical growth of the point counting problem in these sets. So again, just think of balls as a first approximation. So the left-hand side is the number of points that your lattice has with a large ball, say a ball of radius t. And Schmidt said the main term grows like the volume, which was known before and follows from the Siegel summation formula. And Schmidt established an error term, which is on the order of the square root of the volume. So the quality of this error term, the fact that we have a power savings, that's what I mean here by effective counting. It's counting with an explicit bound on the error rate. This result of Schmidt from 1960 has not been improved. Even if you talk about Euclidean balls, not just this general, very general setup of an unbounded ordered family. Just take Euclidean balls and count the number of lattice points in Euclidean ball. If you want to know the behavior of the error term for the counting problem in a typical lattice, typical with respect to the natural measure on the space of lattices, that's an open problem, and Schmidt's bound is the best bound known to date. There's a conjecture of Goetze that this can be improved by reducing 2 by subtracting 1 over 2d, if I remember correctly, in the exponent. But that's an open problem, and Schmidt's result is the best possible. And we prove the cut and project analog of this result. So we prove an effective point counting for the RMS measures. We have the same exact error bound because we use the same technique. This involves these Rogers second moment bounds. With the second moment bounds, we're able to get the exact same asymptotic. And I wrote down here what I said earlier. It matches the best known almost every error bounds, even for the special case of lattices and Euclidean balls. Now, this is an almost everywhere result. It's telling you the counting behavior of sets and balls for almost every lattice or for almost every cut and project set, but it doesn't tell you what's going on for a specific one. If you care about a specific one, say the Penrose example or other examples, then there are other techniques. So for example, the Penrose example is better understood using Perron-Frobenius theory and the tiling, the substitution tiling machinery. And this was done in a paper of Solomon. If you talk about the kind of project constructions, you can get a better handle using Fourier techniques and Diophantine approximation for certain explicit lattices. I mean, the cut and project, the data and the cut and project constructions should have certain Diophantine properties, and then you can get certain effective counts. They're not better than this, but they are explicit. I mean, you have explicit examples of cut and project constructions. So this is joint work that I did with Haynes and Kelly. And there's been other work using pattern equivariant cohomology on tiling spaces by Schmieding and Trevino for cut and project sets that have a certain dilation self-similarity under dilations. Okay. Another thing that we are able to do is to count patches. So I showed you earlier when I showed the slide of the Penrose tiling what I mean by a patch. So a patch is you take your original point set, you centered it. If it were instead of you move the center from a point X to the origin, and then you look at the intersection with the ball of radius r, and this is called the R patch centered at X. And obviously, if R is fixed, you may see the same patch again and again at different X's, and you might want to count the appearances of this patch, again, in a large ball. And this counting problem had only been considered up to the point of proving that there was a main term in the asymptotic. So there was a kind of a prescribed order of growth, and this is sort of linked to the question of unique ergodicity. And if you want to get an error term, in other words, if you want to get effective counting, it's kind of like a form of quantitative unique ergodicity for these tiling spaces. And we're able to do that for almost every cut and project set, where almost every is with respect to any RMS measure. So fix an RMS measure, fix any window which satisfies a certain property of small boundary in the sense of upper box dimension. Then you can find a power savings parameter, which is this theta, such that for any patch, you have this order of growth of the patch counting. There's a main term here, and then there's the error term, and the implicit constants in the error term are going to depend on the data. In other words, they depend on delta, on the lambda, on the kind of project set. They depend on the window. They depend on this dimension of the window, of the boundary of the window, and but we get a power savings. And I just wanted to point out that this result has no analog for lattices, simply because for analogues it doesn't make sense to count patches. Every point has the same patch around it. There is no analog question. So this is the first effective counting result for patches that we are aware of. Okay, I see that I managed to fit everything in my time, and that's it for me. Thanks for your attention, and stay healthy.
Yeah, so thank you very much for the very interesting talk. So it's open for discussion. We have some minutes time. So to start the discussion, just a small question from me. The constant C lambda in the Schmidt-like theorem, what is known about that?
So they have an explicit formula.
You have an explicit?
It's not our work. The main term constant was done by several people. I don't remember the names right now. One of them being Moody, but there was earlier work. And it's expressed in terms of the co-volume of the lattice L and in terms of the volume of the window. It's just simple formula. Okay. Yeah.
Thanks. Further, yeah, Nikolai, our next speaker wants to ask a question. So please, you can ask the question. I can open. Yeah, you can.
Yes, I can. Thank you. So, just one question. So, I would like to ask if the results about classification of your measures lead to certain arithmetical corollaries of such a type. If cut and project set is self-similar, then something is algebraic.
Well, it should, and but and this kind of thing has been already done by Meyer. So Meyer has this beautiful theory from the 60s, where he's proving that if you have what we call a cutting project set, Meyer calls it a model set. If you have a model set and it has the property that when you apply a dilation, the model set becomes a subset of itself. He calls this a similarity. Then the coefficient is an algebraic integer, and Meyer gives a lot of restrictions on exactly the algebraic integer that arises. It's part of his beautiful theory. We are not interested in these dilations. We're interested in self-maps which come from the affine group. And in principle, the answer is yes. I mean, it should be detectable. These kinds of things should be detectable from the algebraic data. We haven't done it so far, but I think there's plenty of things of that type which can be done.
Yeah, are you satisfied, Nikolai?
Yes, yes. Completely.
Okay. Thanks for that.
He can't help saying he's satisfied because he's the next speaker and I could ask him a question.
Yeah, of course.